Everyone, we're going to check out our second example of the Metropolis-Hastings algorithm. Again, we're generating a Markov chain that is guaranteed by the construction of the algorithm to converge to our target distribution. In this example, our target distribution is going to be the t-distribution. Here, r is our degrees of freedom, in case you're familiar with this distribution in other settings. So r is our degrees of freedom. Here's our kernel for the distribution. Notice I'm saying proportional. We don't really care about the normalizing constant. That will cancel out. And in this case, let's look at an example of a random walk sampler. So for random walk sampler, that was where our proposal was our current position plus some random error. So let's check it out. We're going to first initialize our chain, set time to be 1, and initialize our chain anywhere on the real line. Doesn't matter. Then we're going to generate our proposed value. First, we need to generate a random error. I'm going to suggest from a normal distribution with mean 0 and variance sigma squared. Your random error does need to be from a symmetric distribution. So we see that here. So that means our proposal is going to be y, our current position, xt, plus that random error. So where we currently are, plus some random error according to a normal distribution, mean 0, variance sigma squared. So if we want to think about our PDF for that, q of y given xt, our current position, is a normal distribution. The mean, so if we add a constant to normal centered at 0, now we've shifted it to be centered at xt. So that's going to be, and actually here let me just say proportional. I don't really care about the normalizing constant, that 1 over square root of 2 sigma squared. We'll forget about that, 2 pi sigma squared. So let's do e, just the kernel part, to the negative. And then my variable in this case is y minus the mean of the distribution. And if you need a reminder here, go back and look up the PDF for the normal distribution. So variable is y. The normal distribution for y is centered at xt, because I've just shifted this z. I've added xt to it, so I've shifted it by that much, squared over 2 sigma squared. So there's my PDF. This is a normal xt sigma squared distribution. So that's y, the distribution of y given xt. All right, so now that I have my proposal, is my current position plus some random error. Let's figure out if we're going to accept or reject that proposal. So y, we accept it with probability rho. Xt, we stay where we are. We reject it with probability 1 minus rho. We have our definition or construction of rho here. So let's look at it for our particular example. So f is our t-distribution. Again, we don't care about the normalizing constant. So first I'm evaluating it at my proposed value. So 1 plus y squared over r, my degrees of freedom, to the negative r plus 1 over 2 power. Sorry, this is a little small. Denominator, same thing, but evaluated at our current position, xt, to the negative r plus 1 over 2. And then I need this piece that has my distribution of the proposal. So if you notice, we wrote that up here. We're going to evaluate it for the variable xt with parameter y. So this is e to the negative variable xt parameter y squared over 2 sigma squared. And then our denominator, e to the negative y minus xt squared over 2 sigma squared. And if you're saying, Dr. Bell, you're writing the same thing down, or these guys, because this is squared, these are the same thing, exactly. That's the point of this random error being symmetric here. This is also happens to be an example of a symmetric proposal. So these guys cancel out my proposals, and I just have this ratio of f of y over f of xt. That idea of, is my proposed value more likely versus my current position more likely? We'll store or update t and return to step 1 and keep going with our chain. So quick idea of what's going on here before we look at the code and the output. Suppose I had a small sigma. So t equals 1. I have my initial position, xt takes on some value. I'm just going to make something up right here. If sigma is small, then that means my z, remember z was from normal 0 sigma squared. If I have a really small error or variability, then I'm not going to get far from 0 when I generated a random normal value here. So this z will also be small, which tells us that our proposed value, y of t, or y, is going to be close to where we currently are. So because this is where we currently are plus a small value, so y will be close to xt because I'm not going to be able to add much to it. So if I have a small sigma, then I'm not going to be going far. It's step 2. I'm going to be, add a teeny random error. It's step 3. It'll be my current position plus some teeny random error. I'm not going to change much. So each step along the way, I'm not going to be able to move very far because sigma is small. My proposed value is going to be real close to where I currently am. On the other hand, if sigma is large, then z, my random error, could be large. Doesn't have to be, but potentially I could generate something, a random error, really far out, which means y, my proposed value, could be far from where I currently reside. So, for example, in my picture here, at time 1, maybe my current position is right here. So y, reminder, is my current position plus z. So if z is this large value, because it's coming from a normal distribution with a large standard deviation, I'm allowed to go out far. So y is going to be my current position plus some far error. So I could be here and potentially go way up here for my second time slot. My third, I could potentially go really far from there as well. Sorry, my x and y axes aren't matching up. Could go really far, and so on. You guys get the idea. I could jump around a lot if sigma is really large. So the goal is that we want to balance this idea. We want to be somewhere in between these two. So we want a balance of how large or small our steps are, and that's defined by sigma. So let's check this out in our coding and plug in some different values of sigma and see the effects. So the actual function itself should look pretty familiar from our previous example. We need to initialize storage for our chain. Our inputs, we need the degrees of freedom for our t distribution. Sigma, I want to explore what happens when I use different values of sigma, our initial position, and how long we're going to run the chain. Also, something different here, I'm going to create a variable k and keep track of how many times I reject my proposed value. Okay, we're going to explore the effects of sigma. Am I taking big steps, small steps on the number of rejections? So the body of our function here looks similar. We're going to propose our value, and I kind of skipped or did this in one step here. Our proposal was we generated z from normal 0 sigma squared, and then y, if you remember, was xt plus z. So we said y was normal xt sigma squared. I've just shifted it by xt, so I just did that in one step. Y is our norm. I want one of those with mean of where I currently am in standard deviation sigma. Then rho, if you recall, the ratio for our proposal distributions or PDFs, those were symmetric and canceled out. So I just had the ratio of my target distribution. So D for the distribution, and then T, it's the T distribution. I'm evaluating at Y, my proposal, need my degrees of freedom, versus my current position, degrees of freedom. And we have that check if with probability rho, I'm going to update xt plus 1, my current position, to where my proposed value is. Or otherwise, with probability 1 minus rho, I'm going to stay where we currently are. And in this case, we're going to update our counter for how many rejections we've had. K is k plus 1. And I'm going to return both of those things this time. X, my number of or the spaces I'm moving through for my chain, and then K, the number of rejections. So let's look at running it and some different bits of output here. So let's just use degrees of freedom as 4, just to be give us an arbitrary number here. Run the chain for 5,000 iterations. And let's explore these different values of sigma. We're going to go from teeny steps, sigma 0.05, all the way up to big steps, sigma of 16. And then our initial position, we'll use the same one in all the chains of 25. So if you remember, we're generating from a T distribution with 4 degrees of freedom. That looks like this. It's centered at 0. It actually doesn't go that far out here. This is kind of our plus or minus 3-ish region, depending on degrees of freedom. So our initial position is going to be way out here at 25. Let's just see what happens. So I'm going to call these random walk 1 through 4, and I'm going to run it exactly the same starting positions and everything. The only thing that changes are my 4 different degrees, standard deviations. So I've run that, and let's check out the percentage of rejected values. So the first one, when I have a really small sigma, I'm barely rejecting anything at all. 0.2% of my proposals are rejected. That makes a whole lot of sense. I'm starting at 0.25, and I'm slowly trying to work my way over here with teeny steps. I'm not going to reject those. Versus up here, I'm rejecting almost 90% of them. Because I might get here quickly, but once I'm here, I'm going to be able to generate wild values really far from here that won't be any better than where I currently am. So I'm going to reject a lot of those. So we have that range here. And there's kind of a general guideline or rough suggestion here that we want to see somewhere ideally between 15 and 50% values rejected. So I'll just say suggestion. We are looking for 15% to 20 or to 50% rejected. And there's some good reasons for those guidelines or suggestions. Again, too small of a proportion, then we're not getting anywhere close to where we need to be. Too big, and we're just generating a bunch of wild values that we're rejecting. So we need somewhere kind of in between that. So at the moment, it looks like our third value for standard deviation kind of meets that criteria, or sigma of 2. Okay. So some of this code, you guys are getting comfortable enough with this, and I've commented enough, you can figure it out. But I'm going to give some plots in a little bit of our random walk and our Markov chain. And just for reference, I'm going to have some bands on there for 95% values for the T distribution. So hopefully our chain should live mostly within those. All right, so let's take a look at the chain here. And again, I'm going to skip over a little bit of the code since you guys are familiar with that. And let's look at first the plots of our results. So you can see this first one is our teeny tiny steps, and we're starting at sigma of 0.05, so our teeny tiny steps. And we notice we started at initial position of 25, and we're just making really, really tiny steps. And after 5,000 steps, we're still nowhere near being between symmetric values generated between around 0, what we expect for the t distribution. So for this one, I'll just make a comment here. Sigma too small, taking small steps so we have not moved far from our initial position, far from x naught of 25. This chain has not even converged. We're still just taking tiny steps here and there. Okay, the one next to this was sigma of 0.5. So this is better. Remember, here's our 95% bands for the t distribution. 95% bands for t with degrees of freedom 4. And we can see, starting at 25, we take little steps, but they're not so tiny that by around 1,000, we've actually gotten to generate samples from that stationary distribution. So it takes a little bit of time to get there, but we do eventually get there. The next one was the one that looked kind of ideal earlier, and we definitely see that, sigma equals 2. We start at 25, and we actually get there pretty quickly. We don't waste 1,000 steps trying to actually have our chain converge to that stationary distribution. We do get there pretty quickly, and you'll notice this is what we expect. Our samples are symmetric around 0. Remember our goal here, we want a chain that converges to samples from the t distribution centered at 0, and that's exactly what we're getting in this one. And then the third one was, the fourth one was our sigma is too large. And you can actually see, even though the scale is tremendous, 0 to 5,000, if you look closely enough, you can see some spots like this one where we actually have that flat line. We haven't converged, or we haven't accepted a single value in a long time. On this scale, that's probably like 100 proposals almost, and we haven't accepted a single one because sigma is very large, and we can generate some really wild proposals that are far outside of our target distribution. So here I'll just add that note here. Long periods with wild proposals. That were all rejected. Okay, and again, you can see that in lots of places here where you have those flat parts where a chain is staying in the same state. We have not accepted anything for a while. So even though it does lie in this region we want, we're not getting the richness and diversity of samples because we have all these crazy proposals we keep rejecting. So again, balance between not moving anywhere versus getting there and just staying in the same spot because we have these crazy wild proposals. So again, this one was our recommended. Based on the plot, you saw in our first example, it looked like all this crazy noise. That's ideal, that's lovely, that's what we hope to see. All right, back up here, I just want to mention this idea of burn-in period. So you'll see here in the second bit, remove the burn-in period. That's that first bit while the chain is kind of wandering around before it finds its stationary distribution. So it's common practice to just to toss out and remove the first 1,000 or 10,000, depending on how long you run your chain, how long it takes to converge. So for example, this section, if you want to do anything with your samples, you want to toss out this part. Toss out burn-in period. Where you're still waiting to converge to that stationary distribution. So remove those, and then you've got your samples from your stationary or target distribution that you can do inference with, or whatever your goal is. So up here, that's the last part. We've tossed out removed the samples from the burn-in period, the first 1,000 in all of these chains. And then maybe we want to see how closely they match this theoretical quantiles from the t-distribution, so 5, 10, 20, so on up to 95%. And here's the quantiles from the chains we've developed once we toss out the burn-in period. No surprise here, when we have a small sigma, we didn't really get anywhere. Our quantiles are all around our initial position. Starts looking better for these guys. And again, especially this one was our ideal, and you'll notice it matches fairly closely with those theoretical quantiles. Last comment on this section, suppose you want to know if your chain's converged. One way to do that is check out these plots that we've mentioned. You'll see if it's converged like this. Another idea is called the Gelman-Rubin method, where you run multiple chains and see if they're going to the same point. So I'm not going to go over that because of timing in here. I'll just add it as a little footnote here. Check convergence. And one method again for doing that is Gelman-Rubin, if you want to look into that on your own time. All right, that concludes our second example. We'll get into our final example in the next video, and this one will involve Bayesian statistics. So we'll do a quick review of that, or introduction of that, before our final example.